Okay, welcome back for part 2 of our 2D collision example. In the first part, we derived these two equations for the total vertical momentum and the total horizontal momentum. We used the conservation of total linear momentum to get to this point and cancel out the masses. And we also pointed out that there are some givens and some unknowns in each one of these equations. Specifically, the unknowns are v1 and v2, and we see those in both of the equations. And this value psi, that's the deflection angle for our second proton. Uh, so looking at this situation, what I'd really like to do is get rid of psi through some kind of substitution or elimination or something. And my plan is to do that with a trig identity that you're probably very familiar, is that sine squared of some angle plus cosine squared of some angle is equal to 1. And while this might not seem super obvious, when you see how it works out, it actually works out really nice for this problem. Okay, so you're going to notice that we don't have any sines or cosines squared anywhere in either one of our equations. So we're going to get those. We're going to get by squaring both of our equations. We'll start over here on the left side, and we'll square both sides of our vertical momentum equations. All right, and when I do that, I get v2 squared times the sine of psi is equal to v1 squared times the sine of theta. Now over here on the right side, I'm trying to get this psi, so I'm going to first rearrange, and I'm going to get v2 cosine psi is equal to v1 naught minus v1 cosine of theta. And then I'm going to do the same thing and square both sides of this. Sorry, this should be sine squared, and this should be sine squared over on the left side. And when I square that, on the left side, I have the easy one. It's v2 squared cosine squared psi. But on the right side, I'm actually going to have to FOIL this thing. So after I get done foiling, I get v1 naught squared minus 2 v1 naught v1 cosine theta plus v1 squared cosine squared theta. And while it looks like I just made a gigantic mess out of these two equations, I actually did something really slick here. All right. And the slick thing that I did was that I now have a sine squared for this psi term and a cosine squared for this psi term. So what I'm literally going to do is add these two equations together. All right. I'm going to start with the left side, this v2 squared sine psi, plus the left side on this side, v2 squared cosine squared psi. All right. So what do I get? I get v2 squared sine squared psi plus v2 squared cosine squared psi. And then I get an equal sign. So I literally just added the two left sides of the equation. And I'm going to do the same thing on the right side of the equation with these parts, v1 squared sine theta squared, and this entire mess right here. All right. And that'll go on the right side of my equation. And I know this looks horrible, but look at what happened on the left side. If I factor out a v2 squared, then on this side I get v2 squared times sine squared psi plus cosine squared psi, which we know is just equal to 1. So the whole left side really just reduces here to v2 squared. Boy, that's pretty awesome, isn't it? So thanks to that one little trig identity, we just really simplified things, at least here on the left side. But I want to point out another one. Look over here on the right side. If it works for psi, it works for theta too. So I can simplify over on the right side there as well. I can factor out the v1 squared from those two terms. And again, it'll be multiplied by 1. So I just end up with a v1 squared plus 2 v1 naught v1 cosine theta, all just hanging out there on the right. And this is a rocking equation. Now, how much better is it really? Well, it's pretty considerably better. We've kind of lost some signs in there, right? And we don't have any squares left, but also we really don't have psi left anywhere in the equation. So we're left with just two unknowns, v1 and v2, in this equation. So now we're down to that last thing. We need one more equation to be able to solve this problem, and we're going to use the conservation of total kinetic energy before and after the collision to help us out with that. So we're going to use this last equation and that in the next video.